Good day. For those of you who do not know us, we're the instructional staff for ECE 150. Professors Hiren Patel and Werner Dietl and Douglas Harder. In this topic, we're going to look at the call stack. So, in this lesson, we will start by describing instructions and constants. We will then give an overview of main memory, and we will look at how a program is loaded into main memory. We will observe where instructions, constants, but more importantly, local variables are stored in main memory when a program is running. We will learn about the call stack that is used to store local variables. Now, up until now, we have authored, compiled, and executed programs. Now, how does this actually work? So that's what we're going to look at right now. Now, there are many solutions to the question we are asking right now. So the solution we are presenting right now is a straightforward and very common solution, but it is definitely not the only solution. The solution we're looking at right now is something that uses something called the von Neumann architecture. However, there are other variations or approaches to this problem as well. However, it's a nice introduction. So the question is, what happens when we have this program here and we compile it? Well, here I declare a local variable x, which is initialized with a default value, which is 0, and I query the user for that value. I then assign a local variable pi an appropriate value. We calculate x minus pi and assign that to a local variable result. We check if result is less than 0, and if that is true, then we assign result the value of the negated value of result. So in other words, we make the value of result positive. Finally, we conclude by printing out the absolute value of x minus pi is whatever the result is. A program is converted into a sequence of instructions that the computer can execute. These instructions are stored in a file within a file system. A file is a contiguous block of data that is identifiable through a name. If the file contains data that is instructions to be executed, they are often called executable files or simply executables. Now, file systems are generally, but not always, stored in persistent memory. For example, they may be stored in a hard disk drive or a solid-state drive or some form of optical memory. However, they may also be stored as firmware within some form of flash read-only memory. Now, within this file, each instruction has its own address in that memory space. Now, actually looking at real machine instructions at this point is not worth your time or ours. It's just way beyond your scope right now for many of you, especially those of you who have never programmed before. So instead, we're going to give a very high-level approximation as to what's happening. So suppose we compiled that previous program and stored it on the hard drive. Now, in the hard drive, every single instruction is located somewhere else, and each has its own address. So this program is located starting at address 1954. The first instruction says to assign x the value of 0. The next instruction says to call a routine to print a string at address 14. Now, here address 14 is relative to the start of the program. So address 14 is actually at address 1968. We then call a routine to input a double, and we save that to the local variable x. We assign the local variable pi the value stored at address 15. Again, 15 relative to the start of the program. We now perform the arithmetic operation of subtracting the value of pi from x, and whatever that result is, it is assigned to the local variable result. Now we check. If result is not negative, that is, result is 0 or larger, we're going to jump to address 9. That is, address 9 relative to the start. So that would be here, instruction 1963. However, if the result is indeed negative, we will negate the value of result and assign to the local variable result the result of the previous calculation, which is now the positive corresponding number. Now, whether or not at instruction 1960 we jumped to 1963, or we are just executing the body of that conditional, in both cases we execute the next statement, which says call a routine to print the string at address 16, which is the absolute value of x minus pi is equal to whatever it is. We call a routine to print the double x. We call a routine to print an end-of-line character. We set the return value to 0, and then we actually return. This return terminates the execution of this program. Now, when you run a program, the instructions and constants are copied over from the persistent memory into some form of main memory. Main memory is usually volatile, meaning it disappears when the computer is turned off. Not always, but 99.999% of the time. However, main memory is much faster than accessing the same data in persistent memory. To give an example, if we were to compare the time it takes to access data in the cache, a component of main memory in the processor, and accessing that same data on the hard drive, this would be equivalent or analogous in terms of relative time for me deciding to want to read a book, standing up and picking up a book from my bookshelf and sitting back down and opening it up, versus me deciding I'd like to read a book, walking from Waterloo to Ottawa, picking up that book out of the National Archives, walking all the way back to Waterloo, and then sitting down and opening that book. There's a reason Marvin, the paranoid android, is so frustrated when he has to deal with human beings. Now, once the program is loaded into main memory, the processor then starts executing one instruction at a time. So, in main memory, we've loaded the first instruction to address 0, and then subsequent instructions are loaded after that point. We have instructions in red, constants in blue. The question is, we still refer to 3 local variables, x, pi, and result. Question is, where are these stored? Now, one idea is to store the memory for local variables together with the instructions and constants. This used to be done, but there's a serious problem here, because we would essentially therefore have to reserve memory for all local variables, even if it's very unlikely they will ever be used. And so we will see how we will deal with this at some point in the future. But also, we will not be able to perform recursive algorithms or recursive function calls. Now, again, we haven't covered that yet, but these are just some of the problems with storing local variables together with instructions and constants. It is preferred to find a different location in memory in which to store local variables. Usually, the preferred place is at the exact opposite end of main memory. So, if this represents all the memory of the computer, which it doesn't because most computers have at least 4 gigabytes of memory and not just space for 64 instructions. But we have our instructions at the top in red. Our constants follow that in blue, the constants being the literals that are referred to in the program. And then we store the local variables down here at the bottom in something called the call stack. And so down here at the other end of memory, if we store a value in the local variable x, we actually store that value at address 63. The value 3.14 and change is stored to address 62, and the result that is calculated and then printed is stored at address 61. There's a lot of memory between these two, and we are going to use this memory for other features such as function calls and explicit requests for additional memory as necessary. So, following this topic, you now know that programs are sequences of instructions that are built by the compiler. You understand that they must be loaded from persistent memory into main memory to begin executing them. You know that instructions and constants are stored in separate blocks together, usually at the start of main memory. You know that local variables are usually stored at the other end of main memory. They are stored in what we will call the call stack, and the reason for this name will become apparent. You are aware that the remaining memory between these three blocks can also be used by the running program, and we will see in future topics how it is. Here are the references, acknowledgments, the colophon, and a disclaimer. Cheers!